Hello, everyone. I am Ion Stoica. I am a faculty at UC Berkeley, and I am the director of the RISE Lab. I am also a co-founder of Anyscale, Databricks, and Conviva. A few years back at ScaledML, I briefly presented Ray, a distributed system we have developed at Berkeley for the past couple of years. Today, I am going to provide an update on Ray and go a little bit in more depth. The overview of my presentation is as follows. First, I'm going to start with strengths and motivations. Next, I'm going to talk about Ray, then present some use cases of Ray, and I'm going to end up with a few lessons we learned in designing and building Ray. So today, we are witnessing three trends. First, applications are increasingly incorporating AI. Second, AI demands are exploding. And the third, Moore's law has ended. So applications are increasingly becoming AI-centric. Today, almost every application in virtually every industry, like financial industry, healthcare and life sciences, transportation, hospitality, manufacturing, retail, and more, incorporate AI. And while all these applications are incorporating AI computation and storage demands are exploding. This is a famous OpenAI plot which shows the compute demands to train the state-of-the-art machine learning models from 2012 until 2019. The y-axis is a log scale, and basically what this plot shows is that the computation demands to train the state-of-the-art machine learning models have increased 35 times every 18 months. And this trend has continued unabated. Here is another data point from 2020, and that is GPT-3, one of the largest neural network models developed by OpenAI. And this is not only for esoteric application like playing games or things like that. It's also held for industrial application like image processing and natural language processing. And it's not only processing, but it's also memory, which grows in demand. This is another plot showing the number of parameters of the state-of-the-art machine learning models versus time, this time since 2016. Again, the y-axis is a log scale axis. And you can see here, and the largest model to date, which was published earlier this year, it has 1.75 trillion parameters, and it was developed in China by Beijing Institute for Artificial Intelligence. And if you look at the numbers here and you interpolate the growth, since 2016, the number of parameters of these models have increased over 40x times every 18 months. And if you look just at the past 3 years, they increased over 300 times. This is just astounding. At the same time, as you know, the Moore's law has ended. And this shows a plot almost everyone has seen, which is the increase of performance over time for a single CPU core. And it used to be the Moore's law that was stating that the performance is increasing, is doubling every 18 months. But now, in the past few years, per core performance is just increasing a few percent every 18 months at best. So when you put this together, here I am overlaying the increase in the performance and the Moore's for a single CPU and the Moore's law on the same OpenAI plot. And as you can see, the gap is enormous. And actually, even if Moore's law wouldn't have ended, the gap between the demand of these machine learning models and the capabilities of a single core would have been gigantic. An obvious question here is about what about specialized hardware? After all, we are seeing almost every month or every week announcement about new specialized hardware being built by new startups, large chip companies, as well as cloud providers. As expected, the GPUs provide significantly higher performance. And here is a performance increase for the NVIDIA GPUs over years. And here is for TPUs, TensorFlow Processor Units, which is produced by Google. But while performance is much higher than a single CPU, the growth is not much higher than the Moore's law. So in the end, the gap between the demands and the capabilities of this, even of this specialized hardware, is still huge and growing every year. And the same story is true for memory. So here, the memory of the GPUs, state-of-the-art GPUs, NVIDIA GPUs, is increasing just 1.7 times, has increased over 18 months. Again, it's a huge gap. Another way to look at this, it used to be that in 4 years ago, the largest models were fitting on a single GPUs. Today, if you want just to fit the parameter of the single model, you may need hundreds or thousands of GPUs, just 4 years. And the memory constraints is arguably more important than the computation constraints, because for computation, you can always be smarter. You can always innovate on the architecture. You can always specialize the architecture a bit more to target a particular workload. But with memory, you can't do much. You still need the transistor to store 1 bit of information. So these developments, these trends, leaves us no other way to support these workloads but to distribute these workloads. So next, let me switch gears and talk about Ray and how Ray helped to address this problem. So today, machine learning ecosystem is quite disjointed. Now, for each of particular workload, we do have great frameworks, and many of them being distributed frameworks. Like, for instance, for distributed training, we have distributed TensorFlow and PyTorch. For data processing, visualization, we have Spark or Flink. Also for distributed training, we have Horobot and so forth. However, building any of these like end-to-end machine learning application or machine learning platform requires to stitch together this a set of disjoint libraries. And this makes building this application very hard. And it is hard for 3 reasons. First, you need to, when you build the application, you need to deal with different APIs because each of these kind of systems has different APIs. The second, when you deploy the application, you need to manage different distributed systems, which is very hard. And third, they are actually slow because you need to move the data between different systems, and typically moving the data between different systems require you to store the data on a distributed file system or storage system like S3 or HDFS to serialize it, and then again read from that system, distributed storage system, and deserializing it. Very high overhead. So with Ray, our attempt is to take this today's world and move it to this new world in which you have a single universal framework, which is managing the computation and execution. And you support all their workloads, machine learning workloads on top using libraries. So now I'm going to talk a little bit about, give a little bit of history of Ray and dive into details about Ray. So Ray started around in spring of 2016, actually as a class project. And the goal there was to scale distributed training and later reinforcement learning. At that point, we didn't find any existing system to handle well these workloads. In 2017, we released this reinforcement learning library called RLib and high parameter tuning library, RayTune. And in 2019, we founded a company behind to support the open source development and to commercialize Ray. And in 2020, last year, we released Ray version 1.0 and a new library, Ray 7. Now, Ray has a very minimalist API. This is basically the core API, 6 functions. And I'm not going to go into details. I'm going to use some of these functions as examples. But the main point here is that the API is really simple. You can actually learn it in half an hour. So now, I told you that Ray supports all these workloads. So what makes possible for Ray to support these workloads? Well, it turns out that Ray is extremely flexible and powerful. That's why we call it a universal computing framework. And the reason is that it's for, because it has a few unique characteristics. First, Ray takes function and classes, which are the compute abstractions in most programming languages, and instantiates them remotely and transparently. So you can take function and execute it remotely as tasks, and you can take classes and instantiate remotely as actors. In this way, Ray provides support both for stateless computation, essentially this is RPC, and stateful computations, very much like actor frameworks. Second, Ray provides a future abstraction, and the future abstraction enables parallels. Finally, Ray provides an in-memory object store, and the in-memory object store enables passing the arguments and results by reference, which can be quite efficient in a distributed systems. Avoid some unnecessary copies and movement of the data. And all this is provided as an extension of existing languages, not as a new language. So the barrier to learn Ray is very low. And Ray today extends a few languages. The most popular extension is for Python. And this is what I'm going to focus in this presentation, but there are already also front ends of Ray for Java. And in the experimental phase, there is also a front end for C++. So next, let me illustrate these concepts. So let me talk about function, classes, and futures. And for this, I will take you very simple examples. Here on the left-hand side, we have a simple code which reads 2 arrays from 2 files and adds them up. And here it's a simple class implementing just a counter. So basically, we only show here one method which increments that counter. So now these are just Python functions and classes. So in order to execute them remotely with Ray, you just need to add Ray remote to the function or the class you want to instantiate remotely. And when you invoke that function or class, you also add the suffix to the call .remote. Now, another observation here, notice that this remote method calls or remote function calls, they do not return the result itself, but a future to the results, a reference to the result. And this is returned immediately. It's the call remote calls are not blocking. And if you want to get the result, when you want to get the result, you need to call ray.get on the future. So now let me show you a little bit under the hood what happens when you execute this code. And I'm going to focus on the code on the left-hand side, which is remote functions or tasks. So let's assume that we have two nodes and the two files are storing the arrays are stored on these two different nodes. Now, when we call the first remote function to read an array from file 1, Ray is going to instantiate a task. And when we submit this function, we get back immediately a future to the result of this remote function. Okay? And so, and again, the future represents a reference of the result. And this allows us to immediately execute the next call to read the second array from the second file. Again, on submission, as soon as you submit this call, you get immediately back the future to the result. And now you call immediately the next function, which adds the two arrays. And to this function, you pass the references, the futures to the two arrays. This again returns the future to the result, to the sum. So the main point here is the following: that as at this point, when you execute, when you submit all these function calls, Ray just gets a submission request and starts the work to produce, to instantiate the task and to run these tasks. But Ray receives is doing this in parallel and executing this task in parallel, because the program, by submitting all these functions, remote function calls, one after another, without blocking, provides to Ray a view of the entire execution graph. So Ray can intelligently parallelize this execution graph. And when the programmer wants to get back the result and it calls a get, now this is the only function which blocks. And now you block until all this execution graph is going to run, to complete, and produce the result. Okay. Ray has also support for a specialized hardware and for heterogeneous resources. When you declare a function or you invoke a function or a method, you can actually specify the number of CPUs, GPUs, memory for that function or method. So now we've seen that Ray can provide support for both stateless and stateful computations, and provides future abstraction which enables parallelism. Next, let me talk about the in-memory object store. So let me start and to provide a motivation for the in-memory object store. Here it's an RPC example, a remote procedure call. And I'm showing that because there is a core, actually tasks they implemented an RPC abstraction. And RPC is extremely popular abstractions. It's used now in virtually every distributed system. And here is a simple example in which we create an array, then a matrix, then we take the inverse of that matrix, and then we square the result. And the inverse of that matrix, it's execute on node 2, and squaring that matrix execute on node 3. So in this case, typically, this is what happens under the hood. Node 1, when invokes the inverse on the matrix, is going to send the x, the argument, to execute the inverse call on node 2. When this inverse function ends, it sends back the result. Let's say it's y. Node 1 then takes y and passes it as an argument to the square function, which shifts the argument y to node 3, is squaring matrix y, and send back the result. Now, the main point here to note is that y is shifted between node 2 and node 1, and then from node 1 to node 2. But node 1 doesn't really need y. It doesn't do anything with it. The only thing it does is to pass it around to node 3. Now, let's look what happens in Ray. So Ray provides also an object store. So when you create an object in Ray, this object is put in the object store. And you get a reference to this object. So now X is stored in the object store for node 1, and it returns the reference is XID. Now with Ray, when now you invoke from node 1 the inverse function, you send the argument to node 2 the reference to X instead of X itself. Now, at node 2, when you execute the inverse function, you don't have the X, you have only the reference, so you are going to transfer X to node 2. You are going to square it, but when you produce the result, the result is going to again be stored in the object store. And as a result, you send back the reference to the result, YID. Now node 1 takes the reference to y and invokes the square function on node 3 by passing the reference to y. Now node 3 executes square, finds the square function, and it has a reference to y, then it's going to transfer y. And that transfer is going to happen from node 2. When it gets y, node 3 finally squares it and send back the result, which is a reference to the result to the result ZID. But the main point to notice here that unlike in the previous case, in the RPC case, where y was sent to node 1 just to be sent to node 3, in this case, y is shipped only between node 2 and node 3. So instead of moving y twice, we move y only once. So we save a movement of y by using the in-memory object store of Ray and passing the argument by reference. So here is a Ray architecture, and this is the original architecture. In the end, I am going to talk about some improvements we made to the original architecture. So Ray has, like many other systems, distributed systems, has a driver which executes the code, and then has workers which are going to run the function, remote functions, and also has actors which are an instantiation of a class. In addition, has the object store, as I mentioned earlier. To be very clear, the object store is only storing immutable objects. The objects are immutable. They are not mutable. And immutability makes it much easier to manage the object store, to maintain the consistency of the data. And then Ray has a distributed scheduler. In particular, when a driver or a worker or an actor submit a remote call, this is going to the scheduler. And the scheduler decides where to run the remote call. If it's a remote function, it's going to find a node which has the resources to satisfy the demands of running that remote functions or task. If it's an actor, if it's a method, then it needs to find the actor to which that method refers to. Okay. The schedulers periodically exchange the information about the resource availability on their nodes. So therefore, each scheduler has a reasonable up-to-date view about the resources available in the entire system, and it uses this information to decide where to instantiate a new actor or to run a new remote function. Finally, Ray has a global control store which keeps the metadata of the computations. It has an object table which keeps the references of the objects and where these objects are stored, on which nodes they are stored, and also keeps a task table which has a lineage of basically the task graph being executed, of the application being executed. So Ray is highly scalable. So it's distributed at all layers. First, it has a distributed scheduler. So the scheduler is not a single point of bottleneck. And also the global control store can be shared. So both the object IDs and task IDs are pseudo random numbers, and it's easy to shard them across multiple instances of the global control store, multiple shards of the global control store. Okay. Finally, unlike many frameworks, today distributed frameworks, where only the driver can instantiate new tasks, with Ray, not only the driver, but also the workers or actors can instantiate new tasks or actors. This way, the driver itself is no longer a bottleneck. Just to give you a sense, if the driver is the only one in the system which can submit the tasks, typically you are going to have, in typical system today, you can only submit maybe a few tens of thousands of tasks per second. But with Ray, there is actually almost no limit. This is no longer a limitation. Because if you want to build, for instance, to submit 1 million tasks per second, and one driver and worker say can submit only 10,000 tasks per second, then you are going to ask 100 workers to submit each 10,000 tasks at the same time, and now you are going to get 1 million tasks per second. Finally, originally Ray provided fault tolerance, and for implementing fault tolerance, we use lineage-based reconstruction. This was done before in systems like Spark, and to some extent MapReduce. And the main idea here is that if you lose an object, an input, you can reconstruct that object by rerunning all the computations which created that object in the first place. And we do so by keeping this lineage or the computation graph which created all these objects in the system in the global control state. Okay. So, and then it's again, when an object is lost, you can go to the global control store and you get the lineage you need to reconstruct that object. So now let me say a little bit about adoption of Ray. Ray has a best-in-class adoption. When you look at one of the metrics, GitHub key metrics, popular metrics, GitHub stars, and this is compared with other distributed frameworks, including Spark, Kafka, Flink, Kubeflow, MFlow, and Dust. And you can see here Ray with dark red has arguably the fastest growth among all. Today is well over 17,000 stars. Ray also counts over 550 contributors, and these contributors contribute not only simple fixes or improve of documentation and things like that, but these are major contributions. Like for instance, Java API, Azure support for cluster launcher, refactor actor management, direct calls between actors to improve the call latency and throughput, refactoring C++ workers, and many more. So far, I talk about Ray, or called Ray Core. But the power of Ray is not really only in its flexibility and simplicity. Actually, the real power of Ray, when it comes to developers, it's in the library ecosystem which runs on top of it. And it's our goal to build the best distributed library ecosystem in the industry on top of Ray. And the reason for that is that it's like what makes, in general, say a program language successful is not necessarily because they are the best architected languages. You can think about maybe Python or Java, and you can debate whether they are the best languages, and there is a lot of debate around that. However, there is no debate is that these languages, they provide a great ecosystem of libraries, and this makes them extremely popular, because now the developers, when they want to implement some functionality, they call to function to a powerful a library, instead of writing thousands lines of, say, Python or Java code. And this is ecosystem which is truly open. While we build a few libraries, we are very happy to welcome and support any third-party library on top of Ray. So now let me take tell you a little bit about the distributed library ecosystem on top of Ray. So it includes a bunch of native libraries. These are libraries we developed. One of them is RLib, and this was the first library we developed on top of Ray and led to actually guided the design of Ray itself. And today, RLib is the most popular scalable reinforcement learning library and has support for PyTorch, TensorFlow, and also includes the largest set of reinforcement learning algorithms. Another libraries we built relatively early is high parameter tuning library called Tune. And this again is the most popular distributed open source high parameter tuning library. And actually this is a quote from Max Pamperla, who is a creator of another very popular high parameter tuning library called HyperOpt. And basically in this quote, he says that as a HyperOpt maintainer, he believes Tune is the clear winner down the road, not only because it's architecture, but because it integrates with everything else and is built on top of Ray. So now you are going to see the theme over and over again in the examples I'm going to give, that one of the strengths of Ray is about unifying these workloads, which is actually one of the main goals when we build Ray in the first place. So it's very nice to see that unification playing a very important role in building the Ray ecosystem. Recently, we also launched Ray Serve. This was last year. And although this is for model serving, and although it's quite a young library, it's already got already has garnered a lot of attention. And there are a few other libraries like ArrayIGD, which is a distributed training library. But like I said, Ray is not about only the libraries we build, it's about third-party libraries. And here, again, we are very open. And this is an illustration in which we have these three libraries like Horovod, HyperOpt, and Optuna are libraries which, at some extent, they do compete with Tune or RayGD, but at the same time, they're also use Ray or Ray-Tune to scale. This is true about HyperOpt and Optuna. They use Ray-Tune as a backend to scale. And also Horovod, which is arguably one of the most, if not the most popular distributed training library, recently was ported on Ray so that it can take advantage of the entire ecosystem of the other libraries which run on top of Ray. Here is an example of a machine learning, a natural language processing library running on top of Ray, Spacey. And also, Ray and its libraries are used by several major cloud providers in building their platforms. In particular, Amazon SageMaker using RLib, Azure Machine Learning, and Model Arts from Huawei. Another great example here is Dask. Dask, as you know, it's a popular distributed Python framework and has a very popular data frame libraries. And Dask also run on top of Ray, so it's using Ray as an execution engine. And when doing so, users get higher scalability and more resilience. And this is simply because the Ray execution engine is more scalable and also has built-in fault tolerance for tasks. Ray also integrates and Raytune and RLib with the popular experimentation tracking platforms like Weight and Bias and MLflow and many more. So now let me tell you a bit about a few interesting use cases of Ray and its libraries. One of the early users of Ray was Ant Financials, or now called Ant Group. And they use Ray in production for the past couple of years to support Double 11 and Double 12. As you probably know, Double 11 is the largest shopping day in history, or in the world. And it's using Ray to build an entire platform. They call it Fusion engine. At the bottom, they use Ray to provide support for different distributed workloads, like streaming, serving. On top of that, they have a bunch of modules implementing different popular algorithms. And on top of that, they have a bunch of services and applications in different verticals, like marketing, advertising, recommendation, and search. And here, it's a code from Ant, basically saying we build streaming, serving, and iterative calculation based on Ray. And the solution based on Ray has been running stably in Ant Group, successfully supporting large-scale activities such as Double 11 and Double 12. And today, if I remember correctly, the largest deployment of Ray in Ant counts 200,000 cores. Here is another example, Uber. As you know, Uber is one of the pioneers of the machine learning platforms with the release of Michelangelo a few years back. Now, Uber has decided that the new machine learning platform they build internally, called Canvas, is going to be built on top of Ray. And the reason for that, it's reflecting in this code. We believe that Ray will continue to play an increasingly important role in bringing much needed common infrastructure and standardization to the production machine learning ecosystem, both within Uber and the industry at large. And more, they say, by leveraging Ray, we can combine the pre-processing, distributed training, and high-parameter search, all within a single job running a single training script. Again, you see the same theme of unification and of the library ecosystem as some of the key advantages and benefits provided by Ray. And here is a more fun example, different one. And this is Quantum Black, McKinsey company, use RLib to design the boat of New Zealand to compete in America's Cup. They also use AI Sailor. They use RLib to implement AI Sailor to help the team, the Sailor team, to train. So anyway, as you probably know, the New Zealand team won the America's Cup. And America's Cup, it's the most prestigious sailing competition, dating all the way since 1841. So very happy with the outcome, of course. So finally, I'm going to end up with a few lessons we learned in our journey to develop Ray. And a lot of lessons were obviously based on the interaction with our users and based on their feedback and trying to solve their problems. Now, at a high level, at least for the workload supported by Ray, one general lesson we learned is that the developers care more about functionality and performance than fault tolerance or even debuggability. When we started Ray, we had provided only the task abstraction, only the stateless computation. Okay? And this is a very elegant abstraction because what it's doing is just taking some input, perform some computation, and provides an output. Has no side effects, stateless, like I mentioned. So it's easy to provide fault tolerance by re-executing the computations. All the state is external. And easy to debug because, again, there are no side effects. Unfortunately, it turns out that we had to address a few pretty hard challenges. So one is performance. Obviously, when you train machine learning models, neural models, you use GPUs or you do inference. And with tasks, this is hard because remember, they are stateless. So therefore, you need to bring in the data. But bringing the data from even when the data is in the memory of the CPU to move it to the GPU's memory, it's expensive. And then you need to initialize the environment like TensorFlow to run the computation, even more expensive. Another problem, it turns out, is functionality. With reinforcement learning, we need to do simulations, like if you do gaming or if you use a simulator, like a board simulator. But many of these simulators are closed source. And because they're closed source, you cannot get the data out of them. And because you cannot get data out of them, you cannot execute them as stateless, using stateless tasks. For all these reasons, we had to add actors. And now actors have internal state. This means they have side effects, much harder to debug, much harder to ensure fault tolerance. And that was not enough. When we provided actors, the actor abstraction for the first time, we allow only the creator of an actor to invoke methods on that actor. Okay? And that simplifies the design a bit, but we can't hold the line because people wanted to implement things like parameter server. So there, some worker creates an actor to hold the state, but then multiple other workers, they have to access that state in the parameter server. So you need to pass them the handle of the actor to the other workers so that they can access the state in the parameter server actor. Okay? So you had to pass the actor handles around. And now things are even more complicated because you are going to, not only that you have internal state of the actor, so the computation are not side effect free, but you are going to have multiple concurrent. You can have multiple concurrent invocation of the same actors. So then what is the story then? What is about fault tolerance for actors? What can you do? Initially, we are very ambitious. We wanted to provide fault tolerance not only for tasks, but for actors as well. And the way we do it, we wanted also to provide it transparently. for the programmer. So basically, you're doing periodic checkpointing of the state under the hood, and then replaying if you have an actor fails to reconstruct the internal state as well as outputs of its method invocations. It was very elaborated solution. We are pretty proud about it. Unfortunately, after a while, we gave up on it, and that's for 3 reasons. Users, for performance reasons, started to use multi-threading, and now you have non-deterministic methods, right? You cannot serialize them, even the invocation of method of the same actor. Second, it was prohibitive overhead when you reconstruct for stateless actors. Actually, there are actors, like for instance, when you do model serving, the model doesn't change. You just load the model, and then you serve the request on that model. So if you fail, there is no expensive state to reconstruct. You just read again the model. So a general solution for this simple example was prohibitively expensive. And then it's actually you can reach application deadlocks. And here is an example. Say you run training on 8 actors, 8 nodes, using gang scheduling. So everything is scheduled at the same time, and in order to make progress. And now one actor fails. Now, if an actor fails, even if you have transparent fault tolerance, you cannot make progress because you don't have enough resources in the system. You need 8, but you have only 7. So you are stuck. Of course, the application can recover from that, right? By basically saying, take a previous, make a checkpoint, application level checkpoint, and then restart from that checkpoint, but now using only 6 or 7 actors or nodes to do the training instead of 8. So as a result, because of these limitations and challenges, we decided to ensure only automatically restart of the actors and let the application deal with checkpointing and recovery. Now, let me say a little bit about the object reconstruction. So again, when the object is lost, we want to reconstruct it. And this refers, what I'm going to talk now, refers to objects created by tasks. And there are many questions here. It's about how you detect the failures. It's not trivial. And if you detect the failures, who is doing reconstruction? If there are many workers accessing the same object, and that object is lost, which of these workers is going to invoke that reconstruction? How do you avoid multiple reconstruction of the same object happening at the same time? The original design was to rely on this global control store, which gives the information about where each object is created and where it is stored and things like that, to address these challenges. However, having to keep the data consistent in this global control store for all objects at all times is expensive, can become a bottleneck, introduces latency. So instead, we moved to another model, which we call ownership. And the idea here is to distribute the metadata about the object across the workers, across the nodes. And the main idea here is a worker who owns the future of an object owns the metadata associated with that object. So say if worker W submits a remote function, f.remote, which creates the object X, W owns X metadata. W will be in charge with reconstructing X. So therefore, when X is lost, W will reconstruct it. And also use actor supervision. So if a parent actor fails, we kill all its children, all the actors it created. This is for simplicity. Actor supervision, it's a popular technique to handle fault tolerance in the actor systems. So in some sense, to summarize, the ownership help us to maintain the following invariant. An object is reachable and can be reconstructed as long as its owner is alive. So basically, we enforce the phase sharing between the owner and the object. Now, the final example I have here. Flexible this is about scheduling. So Ray support a variety of workloads, support a variety of applications. And not surprisingly, different applications require different scheduling policies. You may want affinity, okay? You may want a task and an actor to be collocated, right? For instance, an actor which is training a policy on the GPU, and a task or an actor which is doing rollouts using that policy for a reinforcement learning application. You may want anti-affinity. You may want to have, when you do training, you want to have different workers to run on different nodes. You may want gang scheduling, like I mentioned. When you train, you may want the workers to go into lockstep. So all the workers have to be active at the same time. You may want data locality. You execute a computation of the data is. So how do you design a scheduler that is so flexible, and not only flexible, evolvable? Because I'm just telling you about some examples we've seen, but always there are new examples and new policies people want to implement we haven't thought about. So to address this problem, we added to Ray this concept of ephemeral resources. So Ray fundamentally provides resource constraint scheduling. This means that if a task or an actor specifies the resources it needs, then Ray will make sure to schedule this task and actor on a node which satisfies resource requirements of that actor or task. But in addition, we add this concept of ephemeral resources which gives the programmer to dynamically create, modify, and delete logical resources. And by doing so, you can actually implement arbitrary scheduling policies. And let me give you an example here. Say we want to provide data locality. Say we have a remote function G, which creates an object X, which is stored locally. And we want another function F, which is going to operate on X, to be executed on node 2, local, to be on the same node where the input, its input is available. So in order to enforce that policy, G will also create an ephemeral resource on node 2 with capacity 1, call it XR. And now, say we execute remote function F, and again, we want this F to run on node 2, where its argument is stored. Then we can use options to specify this, that this remote function also requires the ephemeral resource XR, 1 unit of that. And then under the hood, Ray treats ephemeral resources like regular resources, and is going to find a node for F to meet all the resource constraints. In this case, also it needs to meet the ephemeral resource constraint for XR, and node 2 is the only one who has ephemeral resource XR. So therefore, F will be scheduled on node 2. Okay. There are many other lessons. A few of them I'm listing here, but I'm not going to go into details. First of all, the API proved surprisingly stable, the Ray API. There are virtually no changes to the core API for the past 3 years. And we attribute that to its simplicity. Now, the second thing is that we are very proud that about this API, so it's very simple, very easy to learn. However, a simple API might make distributed computing easier, but not necessarily easy. Because building arbitrarily parallel programs is fundamentally hard. Because, as you know, humans are much better at thinking sequentially than concurrently or in parallel. As such, most users use Ray via libraries, libraries which abstracts away the parallelism. And the last lesson, there are many cluster management there for distributed systems. But it turns out that this managing the clusters is still a pain. And as such, surprisingly for us, one of the most loved features of Ray is Autoscaler, which is a Ray's cluster manager, which also provides auto-scaling capabilities. So with this, let me conclude. So in this talk, I argued the distributed, and in particular distributed AI applications are becoming the norm, and this is because the demands of these applications are growing much faster than the capabilities of a single node or a single processor. So there is no way to scale or to support this application than distributing these applications. Second, building distributed applications is really hard. And finally, I hoped that I convince you that Ray is a promising universal framework that can simplify building distributed applications. Thank you very much.